All right, welcome to The Explainer. Today, we are diving into the absolutely wild 75-year journey of artificial intelligence. I mean, it's a story that's packed with brilliant minds, some really crushing setbacks, and of course, breakthroughs that are literally changing our world as we speak. So, let's get right into it.
Okay, to really get a feel for how far we've come, you just have to look at this comparison, right? On the one hand, you've got IBM's Deep Blue back in 1997, an absolute beast of a machine for its time. But here's the thing. It was built to do exactly one thing, play chess, and that's it. Then, on the other hand, you have GPT-4. This thing doesn't just master a game. It masters language, logic. It can even reason about what it sees in an image. It can pass the bar exam and then turn around and write you a poem about it. This is not just an upgrade. We're talking about a fundamentally different kind of intelligence.
So that's the big question, right? What on earth happened in the years between these two? How did we jump from a super specialized chess machine to something that can reason about, well, almost anything? That's the story we're going to unpack today, and we'll do it by looking at three totally distinct eras of AI. Okay, so our story kicks off in what we call the Age of Rules. The core idea back then was, well, it was beautifully simple, maybe a little naive in hindsight. People basically thought that intelligence was like a giant instruction manual. The thinking was, if we could just write down all the rules for thinking, we could just feed them into a machine, and poof, intelligence. And this whole dream really got its start at the legendary Dartmouth conference back in 1956. The pioneers there made this incredibly bold proposal. They truly believed that every single little aspect of learning and intelligence could be described so precisely that you could just code it. They honestly thought they might crack the entire problem in a single summer. Yeah, let's just say they were a little optimistic. This whole philosophy led to the very first real AI boom, and it was powered by something called expert systems. The idea was to build a program that could copy the decision-making of a human expert. So, for example, there's this famous system in medicine called MYCIN. It had over 600 if-then rules that doctors wrote out by hand. You know, like, if the patient has the symptom and that lab result, then you should probably consider this disease. And the crazy thing is, it kind of worked. In some tests, it was actually better than junior doctors. But, and this is a huge but, this is where it all fell apart. This slide shows the fatal flaw, what became known as the knowledge bottleneck. Just look at how the number of rules you need just explodes. The real world is just too complex, too messy. You can't write a rule for every single possibility. This whole approach was just too brittle. And that brittleness led to broken promises, which led to funding getting pulled. And that plunged the entire field into the very first AI winter. So coming out of that AI winter, the lesson was crystal clear. You cannot hand code intelligence. It's just not going to work. So the entire field had to pivot. And this brings us to the second era, the age of learning. The thinking completely flipped. Instead of giving machines the rules, what if we just give them tons of data and let them figure out the rules on their own? The real key that unlocked all of this was an algorithm called backpropagation. And the idea behind it is actually pretty simple when you break it down. Imagine a neural network looks at a picture and makes a guess. That's a dog. Then you tell it, nope, sorry, that's a cat. The network measures how wrong it was, that's the error, and then it sends that error signal backward through all its connections, tweaking each one just a tiny bit to make it more likely to say cat next time it sees something similar. Now do that millions and millions of times, and the network slowly but surely teaches itself how to see. And this slide right here shows what was basically the big bang moment for modern AI. For years, getting computers to recognize images was this slow, grinding process. You can see the error rate barely budging. And then, 2012 happened. A deep learning model called AlexNet enters the big ImageNet competition. And just look at that drop in the error rate. It's a cliff. AlexNet didn't just win, it absolutely destroyed the competition. It was definitive proof that this new way of thinking, deep learning, powered by massive graphics cards, was the future. Okay, so vision was making huge leaps. But language was still a huge problem. See, the models at the time, called RNNs, had a major flaw. They had to read text one word at a time, in order. It's like trying to understand a book by reading it through a tiny pinhole. By the time you get to the end of a long paragraph, you've completely forgotten how it started. The models just had terrible short-term memory. It was a fundamental bottleneck. And that bottleneck, that memory problem, is what sets the stage perfectly for our third and current era of AI, an era that was kicked off by a single absolutely revolutionary research paper. This is the transformer revolution, and it's all about one core idea that changed, well, pretty much everything. So, in 2017, some researchers at Google published a paper with this almost cocky, playful title, Attention is All You Need. This paper introduced the transformer architecture, and I am not exaggerating when I say that pretty much all of modern AI, ChatGPT, Midjourney, all of it is built on the ideas in this single document. So what is this attention thing they're talking about? Let's use a super simple example to get our heads around it. Take this sentence. The animal didn't cross the street because it was too tired. Now, for an AI, the big question is, what does that word it actually refer to? The animal or the street? Okay, so here's the magic. Instead of reading one word at a time, a transformer looks at the entire sentence all at once. And because of that, it can learn to draw a direct connection, to pay attention, between the word it and the word animal, no matter how far apart they are. This ability to weigh the importance of every word in relation to every other word completely solved that memory problem. This was the breakthrough. This is what made things like GPT possible. And that brings us right up to the GPT models that we all know today. Once OpenAI had the transformer architecture, they basically started a relentless campaign of just one thing: scaling, making them bigger and bigger and bigger. Just look at the growth in what they call parameters. Think of them as the knobs the model can tune. We go from 117 million in 2018 to an estimated 1.8 trillion for GPT-4 just 5 years later. The scale is just mind-boggling. Let me just put that in perspective for you. From GPT-1 to the predicted GPT-5, we're talking about a 25,000 times increase in model size in less than a decade. That is the exponential curve that defines the entire modern AI race. But it wasn't just about making the models bigger. The reason ChatGPT became this huge cultural phenomenon was because of another clever trick, RLHF, or reinforcement learning from human feedback. This is basically where they had tons of humans rate the AI's answers. Thumbs up for a good answer, thumbs down for a bad one. And over time, this taught the AI not just to predict text, but to be helpful, to follow instructions, and maybe most importantly, to be safe. This is the secret sauce that turned a raw, powerful engine into the friendly chatbot we all know. Okay, so after this whirlwind tour through 75 years of AI, where does that leave us? What have we actually learned from this history? Let's try and pull out the key patterns of progress because they give us some major clues about where this is all headed. It really boils down to 3 big lessons. First, we have what are called scaling laws. Basically, we found that if you throw more data and more computing power at these models, they just get better in a surprisingly predictable way. Second, there's something researchers call the bitter lesson. And the lesson is that simple algorithms with just a ton of computation almost always beat more clever human-designed systems. Brute force wins. And finally, the most mysterious part, emergent capabilities. This is where completely new skills like being able to write code or do math just appear out of nowhere once a model gets big enough. Nobody explicitly programmed them to do it, they just learn. And this is what leads us to the central, fascinating paradox of AI right now. Because of those scaling laws, we can actually predict the size and general power of the next AI pretty well. We know it's going to be bigger and more capable. But because of those emergent abilities, we have almost no clue what new things it will suddenly be able to do. We can predict the scale, but we can't predict the skills. And that is the question that's driving the entire field forward, leaving all of us to wonder, what new abilities are about to emerge?